So today Project King, she's out of town, so I'm her postdoc. My name is Noor Xu. So I'm basically going to give you the lecture about, on today it's about, lecture 5 on drift diffusion, diffusion as well as carriers generation and recombination. But before I forget, I guess last time we're talking about lectures 4 stuff. It's about carrier mobility as well as drift process. So basically, students asked a lot of questions. So basically, Project King and I, we made a solution. We made a answering to those questions. Basically about like multiple topics. Like for example, some students asked, what about like the phonon limited scattering, so some like velocity saturation stuff. So basically, we're gonna post the solutions online. So basically, you guys should keep eyes on our website. But I know it's unfortunately like our around EE building, we have like some power problems today. So basically, all the EE servers are down right now. So you may come back later, okay? So basically, it's about some explanations of some issues we offer in lecture 4 about carrier drift process, okay? So today, so we're going to continue our discussion about semiconductor transport. In this lecture, we plan to talk about instead of drift process, so drift process, is a carrier's motion, in response to applied, electric field. But today, I would like to talk about some other process, namely, diffusion as well as generation recombination. Those will also contribute to the current mechanisms in the semiconductors. Okay. So let's first think about diffusion process. So actually, in our previous lectures, we talked about drift. Then basically we assume our semiconductor is uniformly doped. So basically we have a uniform carrier concentration throughout the semiconductor, right? So basically from position 1 to point 2, all the carrier concentration kind of uniform. Then basically we just apply electric field. We see the motion of the carriers. But today, we're going to see the problem of, okay, so in most of the cases, due to the like non-uniform doping, something in reality, we always have very non-uniform distributed carriers. Okay, and okay, so for example, in my position 1, I have a higher carrier concentration, could be electron concentration than my position 2. Okay, let's see what else is going to happen here. So at the beginning, I just still like to keep track of a single carrier, let's say single electrons, and if I want to keep track of its motion, so basically it tends just move to all the 3D directions, right? This is actually Brownian motion, right? So basically it's kind of random, it's just due to like the thermal motions, okay? But okay, that's for a single particle. But if I like to keep track of a lot of carriers, let's say multiple carriers, and also over a very sufficient long time. So what I see, eventually I see actually most of the carriers. Okay, so this is a single carriers, single particles. But if I like to keep track of most of the carriers, I just put it here. So basically, you're going to see after a long time, you're going to see most of the carriers, they tend to diffuse from the high concentration side to the lower concentration side. Okay, so you can see this motion is going to happen after a sufficient long time, and actually those are statistics results from most of the carriers. So basically, we call this phenomenon as diffusion. And some students, would like to ask why the diffusion happens, from the high carrier concentration side to the low carrier concentration side. Okay, so to simplify the problem, here we just look into a 1D, it's like one-dimensional semiconductors, or it's actually it's like 1D matters. But then basically initially we have a at t equal to 0, that's at the beginning point, we have a quite non-uniform distribution of the particles. Okay. So for example, at t equal to 0, we have like over 1,000 carriers that just occupy at the very left point, okay? And so basically, and also based on for each particle, actually it's kind of very flexible, right? It can just move into all for the 1D problem, you can just like jump to the right or to the left. But it turns out that for specific finite length semiconductors, the left side is just like close boundary, right? So basically, it's much easier for the carriers just jump to those empty spaces. Okay. So what we're going to do is we're going to see as time evolves, as time increases. So for example, by a feature let's say we'll have a feature time of step of tau. So we're going to see what happens. It's like at t equals to 1 tau as well as 2 tau. So basically, we're going to see is, firstly, we're going to see that those very high non-uniform distribution of the carriers, they start to spread out, okay? And then, just because if you just, you keep track of single carriers, you just tend to jump like both to the left or to the right. But you keep, a track of like many of them. So basically, you see, because they provide more possibility for the carriers to jump to the right. So basically, as time evolves, so basically you can see the very non-uniform peak of the carrier distribution just tend to smear out itself. So basically at t equal to tau, you see it's almost, you have an equal carrier concentration in like position 1 and position 2, okay? And also as t equal to twice of tau and 3 tau, so basically you see the initial very high peak. So basically they start to lower itself concentration, lower the concentration at itself. And then there are more carriers, available carriers, they start to move to the left, to the right. So basically, this process is actually the diffusion process, okay? And eventually, at a sufficient long time, what we're going to see is, so basically, the carriers profiles look very uniform, right? So basically, it got like equally spread it out, okay? So basically, diffusion is something that initially you have very non-uniform profile, but just due to, if you look at the majority of the carriers, just due to, the thermal motion, so after a sufficient time, most of the carriers, they just trying to move from the high concentration end to the low concentration end, okay? So basically, that's qualitatively how diffusion is going to happen, okay? But look here, so as long as we have those carriers diffuse in the space, from the high concentration region to low concentration region. So basically, what happens is like we have a lot of carriers just move in a distance. So then, correspondingly, one can always get some current, just due to those motions. Okay. So here we call this current as diffusion current, and to study this phenomenon quantitatively, we just assume the diffusion current, the corresponding current value. So here is like current density is normalized over the area because we have larger. So think about still the like quasi 1D problem. The larger volume, of course, the more carriers are going to have, and of course, the larger diffusion current is going to have. But let's just normalize over this area because we assume carriers. They're only going to have non-uniform distribution as well as diffusion in this way, along the 1D direction. Okay, so basically we assume in the first order approximation, we assume the current density, the aerial current is proportional to the gradient along the diffusion direction. Okay, so this is kind of 1D approximation. And okay, I'm going to use the case for electrons and holes to explain this formula. Okay, let's just first into the case of electrons. For example, if I have a non-uniform electron concentration versus space versus like the x direction, and turns out, okay, so basically this end, this position is relatively like low concentration. And the other end, what is kind of like, looks like higher, concentration, have higher concentration of electrons, okay? So think about the gradient here, because all the particles, they tend to diffuse from the low concentration end, from the high concentration end to low concentration end, okay? So basically, if you keep track of the majority of the electrons' motion, so basically you're going to tend to diffuse, you're going to move from the right to the left, right, in the negative direction, okay? If we define the positive direction as to the right. And if we keep track of the current generated by this diffusion, because each the electrons, with each electrons with one negative charge, right? So basically, the current is actually, the diffusion current of electrons is actually from the left to the right, okay? So basically, that's a diffusion current caused by, those electrons' motions. So basically, so as you can see here, the last term is basically del n over del x. That tells you about, the gradient here. It's actually the slope, right? So basically, just derive the concentration versus, the positions. And in this situation, because the curves look like a rising shape, so basically we'll have a positive slope here. But okay, so that why it turns out you're going to have, because there's a positive sign also here. So basically, that's why you see electrons diffusion current is in the same direction as the electrons gradient, concentrations gradient, right? The gradient is just like the slope here. Okay, so the current is consistent with the gradient here for electrons case. Okay, so let's look at a case for the holes. Holes are with positive charges, right? So if you look into the gradient of the holes, basically that's a del P over del S term. That's the slope here. That's also, well, the same as electrons, right? It's also have a positive sign. But also, well, the same thing for electrons. The holes also tend to diffuse from the high concentration end to the low concentration end, okay? So basically, that's a flow direction of the holes. But if you think about the current, because the holes holes carry positive charge, so basically, the corresponding current should actually, flow from the right to the left, right? Should flow from the negative direction, which is the opposite case for electrons. So basically, that's why we put a negative sign here in characterizing the diffusion current generated by holes, okay? So basically, just keep in mind that the diffusion current of the holes, they should have the opposite sign as the hole's concentration gradient, okay? But the case for electrons is like, the electrons diffusion current, they just share the same sign as gradient of electrons, just due to the two particles, they have a different opposite signs of charge. So right now, in our first order approximation, we well model the diffusion, the current density is linearly proportional to the gradient for all, for the two types of carriers. So leaving here is so the coefficient here. The first coefficient is like charge Q, right? Because we calculate the electrical current, then we have to multiply the charge. Then leaving a second term looks like a constant. It's a constant. It's independent of carrier concentration as well as for first order approximation, we assume it's like independent of position, but could be changed later. So basically, we call this constant as diffusion constant, or just for simplicity, like diffusivity. Okay. So if you want to keep track of the units that actually got involved in this expression, the current density is the aerial current values, right? It should have a unit of ampere per, for example, like centimeter square. Okay. So the unit of charge is coulomb, right? And the gradient, when we talk about carrier concentration, does have a unit. It's like volume concentration, right? It's like per cubic centimeter, okay? And well, this is just x. This is just length, right? Have a unit of centimeter, okay? So if you rearrange all the units got involved, you could get units of those diffusion constant. So basically, which should display a unit of, okay. So for example, okay. So basically, you see, so current, this is ampere, can be expressed as coulomb per time, right? And this term leaves cubic centimeter minus 4, the total term, okay? So basically, the units for the diffusion constant should be share centimeter square versus time, like say per second, right? This looks like this is coulomb per second, okay? So basically, that's a unit for that coefficient. Just try to balance the units from the left-hand side to the right-hand side, okay? So right now, we are able to model, even in the first order, about the diffusion current got involved in the semiconductor. Just keep in mind, those diffusion current are only going to take place if we have a non-uniform carrier concentration distribution, right? And also by combining the current mechanism we learned from last lecture, that's a drift current. So basically, I'm just going to write expression here. I already have there. So basically, for electrons and holes, the drift current is equal to charge Q times carrier concentration times carrier mobilities, which is defined as also as a ratio between carrier drift velocity over the electric field we apply, and times that lateral electric field. So basically, this just gives us the drift velocity, okay, in the semiconductor devices. Okay, so basically the first term is a drift current, then the second one is diffusion current. So right now, if we just assume there are only two current mechanisms existing in the semiconductor devices, so we are able to combine them. So basically, also I also want to emphasize here is like if you look into the drift current terms, okay, caused by electrical field, for both electrons, this is electrons, and for holes, so basically actually you see the drift current, they always display a positive sign here. This is saying no matter your drift current is caused by electrons or holes, just always follow the direction of your electric field, okay? So basically, the drift current should always have the same sign as you apply electric field, okay? So basically, there's a drift current. But if you look into the second terms, so those are diffusion current, as what I said explained earlier. For electrons, the diffusion current should have the same sign as their concentration gradient. Okay, think about positive slope, then the current also going to flow positively. So basically the case for electrons. But for holes, what actually you will find that is the diffusion current induced by holes, they should just flow the opposite way as a gradient, concentration gradient of holes. Okay, just due to the two carriers, they have the positive, the opposite charge signs. Okay. So right now, let's just look into a very general example of see how we're going to use those equations. I mean like by combining the drift current formula as well as the diffusion current. Let's just see how we use that to solve more general problems. So for here, like what I said, in most of the cases, we're really going to face a semiconductor that have very non-uniform doping. So basically, this is usually the case. Like if you do the doping concentration, if in the device engineering, we do several types of doping. So basically, eventually we get quite non-uniform, some unknown shape, distribution of the doping. So basically, that can give us this kind of non-uniform distribution of the carrier concentration. Okay, let's see if we consider both drift as well as diffusion process in the semiconductor devices with that kind of non-uniform doping. Let's see what happens. Okay, so first, I'd like to confine my case into still at equilibrium case. Okay, so equilibrium means, thermal equilibrium means, there's no current flow through all my semiconductor, right? I could easily like open the terminals. I didn't apply any power supply to semiconductor to generate some apparent current, right? So basically, the current is zero, no current flow. And also, that suggests that, okay, if you look into the Fermi level, EF, so basically it should be flat, right? That's that's how we define equilibrium. So basically, EF is flat due to no current flow as well as equilibrium condition, okay? So basically, that's how I draw here. But just looking into those band structure, based on your knowledge of, carrier concentration versus conduction band energy as well as Fermi levels. So can anyone tell me which position, the left or the right, have higher, let's say, electron concentration? To the left, right? Because you see that actually EF is very close, is closer to the EC in the left end. Okay, I'll call this position 1, this position 2. Okay, so basically, that's how, that's why, I said this semiconductor is fabricated by non-uniform doping, so that I have non-uniform electron concentration from the left to the right, from position 1 to position 2, okay? And position 1, I have higher electron concentration, okay? And in position 2, I have like lower electron concentration, okay? Okay, so based on the diffusion current, I talked about just now. So basically, you see, intuitively, so basically some diffusion, will occur, right, throughout this conductor. So we just roughly think about the direction of those diffusion. Or let's just draw the directions of electrons' motion, okay, without considering about the current direction. Okay, for electrons, for all the particles, right, they tend to diffuse from the high concentration end to low concentration end. So basically, electrons by diffusion, they tend to move from the left to the right? Okay, and also, as you can see, one thing I really forget is if we draw the intrinsic Fermi level, so basically this should be stayed roughly the half of the bandgap of semiconductor, right? Like that, for example, okay? So basically that's intrinsic Fermi level, that's kind of indicator of whether you're going to have a potential difference, whether you're going to have a voltage drop across the semiconductor, right? The same thing as you can see, my band is actually bent here from position 1 to position 2. So basically, you can think that, there's some built-in, there's some electric field, some voltage drop inside, okay? But think about the definition of, let's say let's start from the relationship between potential and energy. My position 1 seems, if you just keep track of EC, seems have a lower electrical potential energy than the position 2. But think about the direction of potential. So basically, I'm going to do here. Okay, so the potential is defined as, for electrons, is actually EC divided by Q and just plus minus sign, right? Because we just keep track of electrons' energy. Electrons will have a negative charge here. Okay, so there's potential between the relationship between potential and EC. And also think about how we define electric field across the semiconductor. Is defined as also minus sign of the gradient of the potential, right? So basically, so looking throughout this semiconductor, from the left to the right, I have increased electron energy, the EC, right? So basically, I'm just going to do here. So basically, electric field is equal to, if you just plug in the potential phi terms, just equal to 1 over Q times the gradient of EC, versus the position, okay? So right now, at position 1, I have a lower EC, lower electron energy, but accordingly, at position 1, I have a higher potential, right? Electrical potential than the position 2. So basically, if you want to draw the direction of the built-in electric field, which is generated by those non-uniform doping as well as those bending, so actually you should point from position 1 to position 2, right? So as you can see, the electric field is proportional, to the gradient of the slope of the EC, okay? So basically, think about the drift current we learned throughout the last lecture. So basically, electrons motion. Think about electrons motion by drift. So actually, this should be in the opposite direction as the electric field, right? This is a high potential. Position 1 is high potential. Position 1 2 is low potential. So basically, electrons tend to attracted by the high potential terminal, right? So basically, that's the flow of electrons by drift under electric field, okay? So right now, as you can see, under an equilibrium state, when my Fermi level is flat, I have a semiconductor bar without any current flow, and also that semiconductor is kind of uniformly doped. Then turns out to be my diffusion current tend to actually counteract with my drift current. So basically, the two current components, they tend to flow in the opposite direction. And also, right now, we want so right now in the following steps, we want to find out actually the voltage difference, potential difference between along the semiconductor to perform some deeper analysis about the relationship between the two. But qualitatively, diffusion current have the opposite sign as drift current at the equilibrium in the equilibrium semiconductors. Okay. Okay. So next thing is let's just do the calculation of the potential difference between the two from position 1 to position 2. Okay. And before we got those, we get into those derivations. Okay. Just think about how we calculate the energy difference between Fermi level and EC. Okay, we can easily start an equation, a relationship between electron concentration as well as, intrinsic carrier concentration, right? So basically, the only difference here is like exponential term. And one easier way to memorize this, I know it's got a lot of energy levels involved. So basically, think about, n-type semiconductor, right? The electron concentration should always be higher than the intrinsic carrier concentration, right? Because this is undoubt, right? So basically, you would expect positive sign here, right? So basically, this should be EF minus EI. And in the n-type semiconductor, EF is always above the level of the intrinsic, half band gap of the semiconductors, right? So basically, that's our starting point. By holding the relationship between the electron concentration and the intrinsic current concentration. And then if we just do the math here, so basically, EF minus EI at the position 1 is equal to KT, times log the ratio of electron concentration and the position 1 over intrinsic current concentration. Assume the band gap, the semiconductor is kind of uniform, right? The band structure, EC and EI, is invariant versus position, right? The only thing changes is the doping. So basically, Ni and position 1 and position 2, as you can see in the future, just share the same value, okay? So, let's just, from this expression, we get actually the energy, the potential energy of the electrons at the position 1, right? Just look like that. This is 1, this is 2, okay? And following the same procedure, we can get electrons' energy at position 2, okay? Which is also a function of the Fermi level, which is kind of flat, as well as the electrons' concentration at this point, okay? So basically, as you can see, if we just compare the difference between the energy at position 1 and 2, it turns out that it's a function of relative electron concentration at the two ends, right? Times constant term is a KT, is a function of temperature, okay? So basically, that's the energy difference. Regarding the potential difference, like what I talked about, right? We should use the energy difference divided by Q, but we have to flip the sign, right? So basically, that's why you see I denote here. So this potential V2 minus V1 is equal to 1 over Q times EI1 minus EI2, okay? So basically, that's how we define the electron's energy, okay? So basically, I want to keep in mind for these slides is as you can see, the potential difference across a non-uniformly doped semiconductor is only a matter of the doping concentration at the two terminals here, at the two points here, okay? Regardless of the doping shape here, like it could be a linear doping, linear gradient, or like parabola shape. It doesn't matter. The voltage difference between the two is only a function of the doping difference at the two ends, okay? Basically, that's going to simplify our problems. And also, we want to get a drift current, so we have to derive the electric field, okay? Build an electric field across the semiconductor, okay? This time, let's start from by writing the relationship between electron concentration as well as NC, the effective density of states from conduction band, okay? And also, I want to talk about like how to memorize this relationship. So basically, as you can see, no matter how high you dop the semiconductor into the N-type, N should always be smaller in values to the NC, right? NC is kind of very huge value. It's like the limit that you can occupy electrons around the bottom of the conduction band, okay? So N should be always smaller than NC, so that's why you see there should be a negative sign here. And by regarding EC is always higher than EF in energy space, right? So EF should always be lower than EC. So basically, this is positive, and this should be negative, okay, to balance the relationship, the relative values, okay? So right now, I want to get a gradient. First, I want to get a gradient of the electrons concentration because those electrons they have a non-uniform distribution, okay? So basically, what I do is I derive N electron concentration versus the space versus the distance x, okay? So think about the equation, the first equation. As we can see, NC and KT and EC, and EF. EF is like flat band, right? EF is constant within the range we are interested. And turns out that it's only EC is depend on the position x, right? As you can see, right? It's like going to change from left to right. Okay, then turns out that this derivation problem is only a matter of how are we going to derive del EC over del X, okay? So basically, you're just following the step to do the math, okay? Turns out to be the gradient is like actually proportional to electron concentration divided by kT times the gradient of conduction band energy. And turns out that the electric field, like what I wrote in the last slides, is 1 over Q times the gradient of conduction band energy versus the distance, okay? Then we can easily rewrite this term as a function of electric field, okay? And so right now, okay, so basically, in that case, we can get those built-in electric field across the semiconductor bar as a function of electrons concentration as well as their concentration gradient by writing, okay, so if you rearrange the terms here, as you can see, it's actually 1 minus kT over Q times actually 1 over N, right, times dN over dx, okay? So basically, that's the electric field when we get in those equilibrium devices. It's a function of electron concentration, which is kind of non-uniform, as well as their gradient, which is also a function of the distance, okay? So far, are there any questions? Okay, great. So if we go back to our problem, our problem is really at thermal equilibrium, then basically the net current flow have to be 0 for both types of carriers, right? For both electrons and holes, okay? So basically, and think about the combined, the comprehensive expression of the, by considering the two current mechanisms. This is like drift, this is like diffusion for electrons and for holes. Like keep in mind there's negative sign here. So we have to balance that to 0. Let's see what we could get, okay? So think about the first term. This is like Q times N times mu N times E. And by using the conclusions we already get, my laptop stopped, and so I just need to reboot that. Okay, so I think I'm gonna write here, okay? Q times N times mu N times electric field, which is equal to, you just look at your notes in the last slide. Q times N times mu N, but the built-in electric field, we're going to write KT over Q times 1 over N times dN over dx, right? For this specific problem, and we have to balance that with a negative part of the diffusion terms, right? Okay, so that's have to be equal to minus Q times dN times the gradient of the electron concentration gradient of electrons, okay? And okay, so if we revisit that, we see that actually we can cancel out most of the terms, right? So the gradient here, as well as electrons concentration, cancel out each other in the drift terms. Okay, what else? Charge Q here. Okay, then the only thing left is like current mobilities. The thermal voltage, KT over Q, is constant, as well as diffusion coefficient, okay? So basically, the relationship got finalized as diffusion constant is equal to KT over Q times carrier mobility, okay? This is actually what we call Einstein relationship, as what I wrote in my title. Are there any questions? Yes? What? Oh, actually, one thing I forgot, one thing I dropped here is that this is a negative sign here, okay? If you look into my derivation about the built-in field, okay? So yeah, those signs also like cancel out each other. It seems my laptop is like, I can never reboot that. Basically, Einstein relationship just tells you just provide you information of how those two current components they relate to each other. And actually, you see the powerful thing of this relationship is like once we know, for example, the parameters from the drift part, like once we know the current mobilities, then we are able to get the diffusion, related parameters like diffusion constant. Okay, so I'll just do for example, for a given semiconductor like this, I have a whole diffusion constant. Okay. Oh, they ask for like whole diffusion constant. They ask for let's do that. Okay. So basically dp, and we already know like the mu p, right? And we know that relationship. So we just times kT over q, which is equal to 410 centimeters squared per volt per second times kT over q is 26 millivolt. Great. Okay. So we can just do simple math. I'll just do that for you. I did that before. So it's 11 centimeter squared per second. Okay. So as you can see, it's consistent with the unit we just talked about. Okay. Okay. So our the final part, one thing I want to add for those, the Einstein relationship is okay. So in most of the cases, we can do approximation, the so-called quasi-neutrality approximation. Okay, I'll just draw still the case of our problem. For example, you have carrier concentration, have a non-uniform distribution like that. Okay. For example, this is just like my ND donor concentration profile. Okay. And this is an n-type semiconductor. N-type semiconductor. Well, the first equation you see here is actually, this is a very rigorous, very strict carrier, concentration neutrality, the charge neutrality rule. So basically, all the charge, ND plus host concentration, those particles with positive charge, no matter mobile or immobile, should be balanced with the charge concentration with the negative signs. Okay. So basically, this is charge neutrality rule. But quasi-neutrality means, okay, we do some small difference compared with this case. It's like we think about those non-uniform doped semiconductors. Actually, they are reached at equilibrium state, so that there's no current flow, right? So in that case, we think that if you want to draw the profile of electrons concentration, it looks like pretty much the same. This is Nx. It looks pretty much the same as the case for the donor concentration. Okay. And okay, this is like N-type semiconductor. The dopants are fully ionized. So basically, it looks pretty much the same because there's a built-in electric field to hold those non-uniform distribution, right? To get a net current flow of 0. Okay? So built-in field tend to stop the diffusion of those carriers from high concentration side to low concentration side. Okay? Okay, so basically by approximating this way, we think those two are actually roughly the same. In that case, so basically electron concentration is just due to NDX minus NAX, right? It could be some erratic, it could be some doping compensation effect, right? So basically, the net doping concentration in N-type material be just equal to electron concentration. And same thing for the P-type material, right? Think about doping compensation effect. So NA minus ND would be just the case, the distribution of the whole concentration. Okay. So in that case, if we go back to the expression of the built-in electric field, so actually we find that, like what I talked about, is a function of Nx as well as the gradient of electrons versus the distance. So basically, we can easily replace that term with Nd, and as well as this term as the slope of Nd. Okay, like that. Okay, so basically, that's something you can do very fast by knowing the doping profiles. It's like Gaussian, error function, whatever, linear doping. So basically, we can calculate the built-in electric field inside the semiconductor in the equilibrium state. Okay. So I think that's so much about diffusion behaviors. Are there any questions? Okay, great. So let's move to our second part. We need to introduce something about generation and recombination. Okay. So previously we talked about drift and diffusion. Just actually those two behaviors is only based on we keep track of the single type of carriers, right? So if you recall like how we derive drift or diffusion, we just keep track of single, let's say, electrons. We see how they behave in the conduction band mainly, as well as we do the case both diffusion and drift for holes. Like, like we separate them. Like we only study the holes case by, most likely around the valence band. Okay, but okay, so basically those are the cases for the diffusion and drift. We only keep track of single type of carriers. But for the generation and recombination case, then we need to consider the interaction between the two types of carriers. So basically, those two processes always involved both electrons and holes. The generation means previously I have nothing in my conduction band and a valence band and a valence band. Then basically, by shining some light or by heating my lattice, by providing some excitation source, I'm able to create electrons in the conduction band, as well as simultaneously, they're going to leave me a hole in the valence band. Okay, so this process is called generation. And the recombination, okay, is by shining some light or hit the lattice, just by providing some energy, right? Need to overcome the gap here. It's like this is EG. The recombination is just the opposite. I already have an electron here. I have another hole sitting here, right? And then at a certain time, the electrons tend to drop some energy and move back to valence to actually annihilate with the holes, okay? So basically, it's going to be nothing left, okay? Both the electron as well as the hole, they're just going to disappear, okay? So basically, this process also going to emit some energy, okay? Could be some shining some light, could be hit the lattice around. Okay, so basically, this is a process of recombination. So basically, you have the idea in mind that generation and recombination, they actually are you got involved with two types of the carriers. Okay, and so right now we want to study the impact of generation and recombination on our current derived. Okay, it may not directly contribute to kind of certain current like magnetism that we see for the drift diffusion, right? It's like J is drift plus J diffuse or something. It may not be contribute a direct term here, but actually, because of generation and recombination, you see that actually that involving carriers concentration change, right? So basically, that's going to modify the term here. Like all the terms related with carrier concentration, you could modify that. So basically, the net effect of those two phenomena, that's could change our both drift and drift and diffusion current. Okay. So let's think about see about more details about generation process that try to create a pair of electrons and holes by providing some energy. The first very simple way is called band-to-band generation. So basically, like what I talked about. Okay. So the process is just a one step, right? You just get some. You just absorb some, your required energy, for example, the band gap here, and just you create a pair of electrons and holes. It's kind of simple. Second type, as you can see, is called this is called RG generation recombination center assisted, or most likely I would call that trap assisted. There's a trap assisted generation recombination that actually requires multiple steps. For example, if I have some energy in my band gap, could be some energy introduced by traps defects as well as very deep dopants. Okay, so basically, to generate an electron-hole pair, so basically I first generate a hole here. Okay, and then the electrons just jump into my trapped energy in the band gap, and the second step, the electron is going to eventually flow into conduction band. Okay, so basically there's a multi-step process compared with single band-to-band. Okay, yes. Actually, there are multiple ways. You could create some defects, okay, as well as you dope some very deep dopants like gold or like copper. As long as they are very shallow, they are not very close to the EC or EV, which are very easy to ionize, right? As long as they are very deep in the band gap, so basically it seems they require some effort, to analyze from here to here. So basically those are deep levels, or we call that trap centers. Okay. The last one, basically, we need to apply a very high electric field. So this always happens at a very high field, electric field. It's called impide ionization. So think about, okay, so if I apply electric field here, then basically I'm going to incline my conduction band this way, right? So electrons in my conduction band, they first travel from here to here, okay? Then basically my electric field is going to accelerate them, right? They're going to have very high connecting energy, and they're going to drop here. So basically, if this energy gap here is larger than 1.5 times the EG is a band gap here, then basically the very kinetic, very energetic electrons, that's going to have a lot of collisions with the lattice, and basically they're going to emit a lot of energies here. Those energies, as long as those energy will be seen by the surrounding holes electrons, they always tend to generate a pair, okay? So those energy are going to be absorbed by those surrounding lattice, and those basically ionize a hole and electron pair. This is called impact ionization, okay? And the opposite process is like recombination. Still going to have the same as direct recombination. You just have electrons coming from conduction band to recombine with the holes in the valence band, just leave nothing there. This is always happens. I would like to add, some other types like 3,5 materials, like gallium arsenide, indium phosphide, something, okay? And the second thing is like RG center trap assisted recombination. Basically, electrons, the first just make a connection here, okay? So basically just stay at the trap levels and wait for a better time, like to get some more energy, more velocity change, and then then basically from the annihilation, from the recombination from the holes jump from the valence band. So basically, the process could be like this, okay? So electrons, holes coming from EC and EV separately, it just meet at some deep levels inside the band gap. Another process, electrons first jump into some trap levels, and then just wait to get more energy, more velocity, and then eventually they're going to come back to the valence band to annihilate with the holes. Yes? Oh, actually, yeah, it depends, because if we just shine some light, we are not sure whether our photon energy is actually exactly to the band gap energy. So basically, that's why this process is actually more, more difficult to happen. But as long as we have those trap centers, so basically first, just by providing or releasing a very smaller energy, we can assist this process, we can trigger this process to happen at a very high probability. So basically, that's the difference between the two, okay? So this RG center assisted, yeah, go ahead.
How does adding energy to an electron in the direct cause it to go to a lower energy?
Well, in that case, in recombination case, well, then basically electrons, they need to emit some energy. Yeah, but for the generation case, if you go back, if you remember in the case for the generation, by inserting those trap centers, then basically we can just provide smaller energy for electron to absorb, right? And then later they're going to trigger the second step. The last one, okay, my laptop did that again. And I'm going to write on the board to explain the last type of recombination. This is called Tsu recombination. This is usually a 3-particle process. Just keep in mind that requires 3 particles. Usually, well, for this case, it's like 2 electrons, plus 1 hole, okay? So Tsu recombination tells you, first I have a available electron in the EC, and I have a available hole at EV, okay? And then, if the electron want to go back, they have to emit some energy, have to drop off some energy. But there happens to be surrounding electrons here. It's very close to the electron which is going to recombine, okay? So basically, once the electrons tend to go back to the conduction band, to valence band, the second electron, the third particle, they start to absorb all the energy within this process, okay? And these 3 electrons go to a very high energy level, go very deep into the conduction band. And the following process, as you can see the step curves here, there, then just take the second electron, a quite long process, to gradually release the energy and go back to the bottom of the EC. Okay, so basically it's called Auger recombination process. This happens at a case if we have very high doping concentration. This is very possible to happen if I have electron. Well, I'm just talking about electrons here. So basically, we have very high electron concentration here. This most likely to happen, or at a very high N-type doping. That's always the case. Because as you can see intuitively, basically you need a lot of surrounding electrons, right? That requires multiple particle interactions, right? Basically, that's the case for Auger recombination. Yes. Yeah, that's the case we talked about in the first column, right? That's band-to-band recombination that happened in the garden arsenide. So basically, as you can see, the first case, right? So basically, in that case, if the electrons just recombine with the hole directly, they could emit some like photons, right, by shining some light. Yeah. Yes. Yeah. Yeah, most likely, this is just based on some facts, right? Based on the material properties. I would say, in the silicon, most of the cases, this process just, don't involve the photon emitting. They don't shining some light. Just going to heat the lattice. So basically, yeah. So basically, that's going to be involve some heating process rather than shining some light. That's the case for silicon. Okay. And also, I don't remember if I added that before. It's like this RG center trap assisted recombination process. This is most of the case for silicon and germanium, those group 4 materials, right? In the group in the fourth column. Okay, so this direct recombination happened at a 3,5 compound semiconductor like gallium arsenide. Okay. So right now, I'd like to explain, actually spend some time, talk about why we have different generation recombination process between 3,5 as well as silicon process. Okay. So first, actually, I'd just like to talk about that there are 2 types of semiconductor materials. The first is called direct bandgap semiconductors. This is called direct bandgap. Second called indirect bandgap. The first one is a case for 3,5 materials, while the other is a case for silicon, germanium, or like group 4 materials. Okay. So so basically, as you can see, well, just intuitively, as you can see, this is E versus K. Okay, this K is something I didn't talk about. When I was an undergraduate, at first I saw this graph, I got very confused, right? Because someone told me this is a band structure of semiconductor materials, but then I just replied, isn't some band structure what I learned before, like just simply as EC and EV versus some space, right? This is the band structure what I learned. But why that turns out to be another second picture of band structure, okay? So I'm not sure whether has Professor King introduced about EK dispersion relationships? Okay, it's fine. Because we're going to provide a separate lecture about, I think should be around lecture 9. We're going to spend some time talk about those EK stuff, okay? So, but just go back to my question, what are the differences compared with the previous concept we proposed for the band structure to study semiconductors? Well, you know that, well, the coordinates are different, but here I like to talk about a K. Has anyone taken some basics about quantum mechanics? Okay, great. Can you explain to us like what the K denotes here? Oh, okay, great. So basically, the K is something like, this we call a reciprocal space, okay? So basically, K, represent momentum, like for example, the velocity, the motion of the electrons. So actually, so think about, well, in the quantum mechanics picture, the momentum of the carriers is actually the Planck constant times the momentum factor. They have the same direction, okay? But this is something that we study for the quantum mechanics, right? Basically, we treat electrons as something between a wavelet as well as a particle, right? It's like quasi-particles, okay? So basically, as you know, if we compare with our previous picture, which we simply draw EC and EV versus space, and compare with here. So basically, the major information we can get from those previous EC, EV versus X picture is that we can get, just for a very simple problem, the most important information here is like the gap in between, right? The value of the EG, okay? So, so if you look into this picture, we could also get that information. So basically, this is the equivalent EC, this is the equivalent EV in the EK plot, okay? We can also get the separation is just a band gap, right? Where we won't have any electron states, appear there. So basically, we can still get information of EG, but the difference is that we get something else. So basically, that's all about the momentum stuff. That's some information we really lack. Something lack from those previous simple EC versus X picture, right? So basically, we can not only get the information of energy as well as position, we can also get information of carrier's momentum. This is momentum, as well as velocity, okay? So basically, this picture provides us more information than before, okay? It's extremely helpful when we try to analyze problems like generation recombination, in the semiconductors, okay? Okay, so let's think about what happens in the direct bandgap semiconductor, like 3-5 materials. So basically, as you can see, this is it's just origin point 0. This is the coordinate is, this is K. Okay, so what happens is like in the 3-5 materials, the conduction band has a minimum at the same K point as valence band. Okay, so what I talk about is like K represents your velocity or momentum. That's to say, you can find the minimum point of electrons, minimum energy of electrons, and the minimum energy of holes at the same K point with the same momentum at the same momentum point. Okay, so basically that's the thing. So basically, if we think about how we trigger generation recombination, for example, recombination, so just take the electrons at the conduction band to emit some energies here, right? For example, in the form of photons. This is actually the light we mean the photons, right? It's also kind of like quasi-particles. It just makes it easier for 3-5 electrons to emit some photons and just get, they want to meet with holes. They just get recombined with holes, okay? So basically, throughout the process, we don't actually require momentum change, right? Because they have the same momentum. They have the same, they appear at the same space, at the same point of the momentum, okay? So this process doesn't require momentum converting something, okay? But it does involve the large energy change you see here. If you just try to move a particle electrons here from here, it just does require a very large emission, a very high energy emission of the photons, okay? So that's a case for direct bandgap semiconductors. If you want to compare to the case of silicon germanium, they call indirect bandgap semiconductors. What do I mean by indirect bandgap design? Indirect means they do not have the same, so basically they do not have EC and EV appear at the same, they don't have them appear at the same K point, okay? So regarding the physics, what happens here is like, if I still want to trigger recombination, I first need some ways to move my electrons here. Okay, I could either do this way or this way. This way plus this step 1 plus this step 2, or I could do it this way like this, right? This is step 1 prime, this is step 2 prime, right? But anyway, since I need to do a lateral shift, right, to transfer my carrier here to here, okay? And that involves both energy as well as momentum change, okay? And this momentum change is actually, let's see, the net shift in the K is actually, you see that I just shift from here to here, they share the same energy, right? So basically there won't be energy change, but just momentum change. This process requires particles called phonons, okay, which compare with photons, okay? Phonon is something like, is a quantized vibration mode or some quantized particles, induced by lattice vibrations, okay? We're going to have more information in the future, okay? So basically that require phonons, as well as the change of energy that require photons. So basically, the indirect bandgap semiconductor, to realize both generation and recombination, we need the help from both phonons as well as photons, okay? Phonon is something that they really don't have energy. So basically, it's like the zero energy change, but they have very large momentum change, okay? So delta K is large. Compared with the case for like photons where the energy change delta E is large, but delta K change is kind of small. Okay, as you can see, well, you don't need like the converter K. Okay, so basically there are the new band structure picture, the new stories, as well as the two categories of semiconductors regarding their generation and recombination process. Okay. Okay, so right now let's think about our carrier concentration affected by those excess carriers. Okay, so previously in the previous lectures, we spent most of our effort on analyzing the two terms. That's at equilibrium state, the carrier concentration for electrons and for holes. Okay, so right now you see, no matter I'm going to bring recombination as well as generation. Okay, I always tend to disturb my equilibrium carrier concentration, right? I tend to like fluctuate those two terms a little, terms a little bit, so that, okay, for example, if you, well, here I denote NP, lowercase np as, this is like the net or the absolute values of my carrier concentration. Just in comparison with like NO and PO, that's a carrier concentration at equilibrium state without those disturbance. Okay, so right now my net, my carrier concentration change, no matter delta N or delta P, just turns out to be is defined actually as the total, the net carrier concentration subtract those equilibrium state, balance, carrier concentration, right? Okay, and also throughout the system, I still need to apply charge neutrality rule so that my delta N should be balanced with delta P, right? Okay? Because those carriers, they are generated by in pairs, right? Once you create an electron, you always create a hole. So basically, those disturbance terms should have the same value between electron and hole, okay? Due to like they just do the things in pairs, okay? And also for here, to derive the styles further, I want to also make an important approximation here. Is what I call low-level injection. So basically that tells about the disturbance, basically delta N and delta P, compared with the equilibrium case, this N0 and P0, is kind of small. It's much lower concentration compared with. So delta N, delta P, as I write here, delta N is equal to delta P, but should be much smaller than my equilibrium state carrier concentration, NO and PO, okay? So in that case, regarding, this is a total, right, net carrier concentration, N is like, delta N plus NO. Because delta N is much smaller compared with NO, so basically, I assume my N is just equal to equilibrium values. It's like NO, but the same case for holes, right? So basically, think about N-type materials. If I assume electron concentration, electrons are majority carriers in N-type materials. That's just equal to equilibrium state electron concentration, which is further dictated by the donor concentration we put into the semiconductor. Okay, this case for the P-type materials is like the total hole concentration should be approximately equal to the equilibrium hole concentration, and is determined by saturated concentration I put in the semiconductors, okay? So basically this is called low-level injection. This is to say that this assumption mainly is made about, my net carrier concentration for certain type of materials, certain type of doping semiconductors should be equal to doping concentration or equilibrium state, majority carrier concentration, okay? In other words, majority carriers will assume they won't get affected by those disturbance, right? Those generation and recombination. They always hold their value as constant as the equilibrium case, okay? However, I should point it out that for minority carrier concentration, that could change by orders, as I'm going to derive the case, okay? So let's first think about the recombination process, okay? So basically, regarding within the recombination process, let's say think about a case for N-type silicon semiconductor sample, okay? So First, okay. First, I have like a light source. I just keep shining on my semiconductors as a beginning time t equal to 0. Okay. So first, okay. So basically, I keep a light shining on the semiconductor so that I could have a constant generation rate. Okay. So I keep generating carriers, and those carriers are out of like off equilibrium. Okay. So basically, before we move further to derive the relationships, let's just look into the recombination rate of holes, okay? Because by shining light, I create electron-hole pairs. So basically, I increase both of them, right? Like by a very large order. So basically, right now I have a lot of excess electrons and holes, okay? But we assume under low-level injection, right? Delta N is much smaller than the real equilibrium, even equilibrium state electron concentration. So basically, this part is negligible. Let's just talk about the role, the impact of delta P we created. Okay, so right now you know that we have like more holes than we have. The balance, the statistics, the interactions between electron and holes, and tend to recombine them. Okay, and it turns out that the recombination rate is proportional to the excess, actually to the hole concentration in semiconductors, right? Because there are more holes, it seems much easier to recombine them. Okay, there's more probability. As well as here, NT is actually, this is a trap concentration. Okay, basically this is a trap concentration. Okay, so basically it tells you about how many defects. Okay, so like what about density of the defects at that inside the gap? Okay. So basically, this is a position where we're going to have ET, right? So basically, for silicon especially, we need those traps to assist us to finish those recombination or generation process. So basically, this tells about the density of the traps here as NT, okay? And then leaving a coefficient, well, this makes sense, right? Because the more traps we provided, then basically we're going to have more chance to finish those generation recombination, okay? And it turns out that there's another coefficient here, tells you about the recombination rate between the product of carriers concentration we're going to recombine as well as the trap concentration here. So this is called capture cross section. Okay, so what this parameter tells us is about how interactive between the electrons and holes actually to recombine or to generate, basically to recombine by putting those, by putting those trap density, those traps in the band gap. It's actually how active, about the recombination process, okay? Because as what I talked about, we could put a lot of types of, dopants like gold, like copper, or create some defects to create those ET. But of course, those atoms, they have different chemical, they are very different in terms of chemical reactions, right? They actually behave quite differently. So basically, this coefficient, just try to benchmark, try to evaluate the properties of those dopants. Tells about how active, how reactive those trap centers are, at a given constant, at a given density of those traps. Okay. So by holding these relationships, so right now think about at the equilibrium case, at steady state case, and also under low level injection. So basically, think about my generation rate. It's kind of like same case like equilibrium, right? Because in my sample right now is under very steady state, right? So also the generation for both electrons and holes should be the same. Okay, so basically, and low level injection also tells us those two have to be balanced each other, right? Because after a sufficient long time, we cannot expect we have an infinite number of holes or infinite number of electrons, right? So basically, once the system will first turn on some light, there'll be some transient behaviors, but after a sufficient long time, then basically those two processes, they should balance each other, right? So basically, in that case, our system will reach at a very steady state, okay? So basically, that tells us equilibrium recombination rate should be balanced with equilibrium generation rate. Should be equal to those two parameters, Cp times Nt times the equilibrium state, carrier concentration, right? For like POO, okay? So in that case, so let's just look into the non-equilibrium case, right? It's about case where we first turn on the light, okay? Regarding the generation rate, this is an equilibrium case, okay? But the thing changes, what's going to happen here? We're going to have net recombination, right? Because we have too many excess carriers. So basically, that's a definition of, the recombination rate introduced by those excess minority carriers, okay? And just turns out to be, so basically the net generation recombination rate is be just proportional to the difference between the net minority carrier concentration rate subtract the equilibrium state minority carrier concentration, right? So basically it's proportional to the disturbance concentration, disturbed concentration that we introduced by heating or like shining some light on those semiconductors, okay? And times multiplied by those coefficients, okay? So here, just for intuitive purpose, so basically we define some equivalent parameter as tau p, which is defined as 1 over those coefficients here. So that would just make things easier. So basically, the net generation recombination rate be just the excess minority carrier concentrations the disturbed carrier, fluctuated carrier concentration divided by that constant, okay? So basically, the reason why we do that, if you look into the left-hand side, is like different derivative versus time, right? It's now del P over del T. And it turns out to be, if we somehow simplify the equation in the right-hand side, basically we share the same form as del concentration over some time constant. Basically, we're going to make the solving the equations easier, okay? So basically, that's how we define, how we come out with the definition of carrier lifetime. Should be, just keep in mind, should be 1 over capture cross-section, describing how interactive, between the electrons and holes, generated by those traps, as well as that trap, the concentration of that specific traps, okay? So basically, actually already talked about, it's like, this is actually a new parameter, new quantities, we call it minority carrier lifetime, okay? So basically, intuitively, we think, those are actually average time of those excess minority carriers that survive inside the silicon region, okay? Before they got recombined within the other types of carriers, before the system reaches the equilibrium state, okay? So basically, regarding the value of tau, as you can see, it's a matter of, the trap density you put here, as well as the trap property here. So basically, it could vary in a very large range from 1 nanosecond to 1 millisecond, okay? And actually, especially for silicon, there are some very typical matters that we can put, to realize those traps, like silicon, platinum, as well as some crystalline defects, okay? Basically, that's about physical meaning, physical sense of those, the parameter, lifetime in the denominator, okay? Into those equations, those dynamic equations, okay? So basically, eventually we got very simple form to describing those, minority carrier excess minority carrier concentration behaviors, which is, the system when the system is off equilibrium state, okay? It turns out to be for electrons in the in the p-type materials, because we're only interested into minority carrier concentration, right? Under low-level injection approximation. For electrons in the p-type materials, so basically we think that, actually we find that del N over del T, in the time domain, the derivative of electrons concentration is equal to injected, excess minority carrier concentration divided by that feature time, right? Divided by a constant. The same thing for holes. The holes concentration in the N-type material will hold a minority carrier concentration in the N-type semiconductors, okay? Turns out that the time domain derivative of that is equal to, okay, is proportional to, minority hole concentration, the hole concentration, minority carrier concentration, hole concentration, excess hole concentration divided by hole's lifetime, okay, another constant. Okay, so I think last couple minutes, I'm just providing an example of how about, well, what a general situation between those equilibrium state carrier concentration with those, off equilibrium excess minority carrier concentration, okay? So simple example, like I have a silicon semiconductor, I dot with 10 to the 16th per cubic centimeter boron. So basically you see there's a p-type. P-type semiconductors, right? So basically I have more holes. Holes are majority carriers, while electrons are minority carriers, okay? So first, I ask you to calculate what are at the equilibrium state, the PO and then what are equilibrium concentration for both types of carriers. For holes, okay, so basically that should be equal to my boron acceptor doping concentration, right? Should be just 10 to the 16th per cubic centimeter, okay? And at the equilibrium state, the product of NP is a constant, is equal to Ni squared, right? That's a junction of law. So basically, NO is just equal to intrinsic carrier concentration squared divided by my hole concentration, right? It'd be just Ni squared over Na. At room temperature, the numerator is like 10 to the 20th, well, this is like 10 to the 16th. So basically, give us 10 to the 4th per cubic centimeter. So basically, the two-time materials have very few electrons, okay? So think about a case for delta N and delta P. And for given a condition like at a steady state, okay? At a constant generation rate of 10 to the 20th per cubic centimeter per second. Okay, so basically, yeah, that's the generation rate. And also given the lifetime of those excess electrons. So basically, as we can see that GL, that's a steady state generation rate, have to be balanced with the recombination rate, okay? Which is the rate for electrons is delta N over delta T, right? Delta T, right? So basically, excess minority carrier concentration, like electron concentration, got disturbed by the generation of the shining light divided by T. This has to be also balanced by delta excess whole carrier concentration versus T. Right? But just in the p-type semiconductors under low-level injection, usually the case we ignore that part, as we can see later, okay? Which should be equal to delta N over some time constant, right? Basically, if you go back to the equation we derived, we reach from the last slide, okay? Okay, so right now, given the generation rate is 10 to the 20th, this is 10 to the 20th, this is like 1 micron seconds, so basically 10 to the minus 6 second, right? So basically, we can get the excess electron concentrations under this condition, right? It's like 10 to the 20th times 10 minus 6, actually 10 to the 14th per cubic centimeters, okay? So basically, that's delta N. Same thing for delta P, okay? Under steady state, when the system reaches a steady state, okay? So right now, let's just calculate the net concentration of electrons and holes. In a p-type semiconductor, like for this case, total hole concentration is excess hole concentration plus equilibrium state hole concentration. For electrons, the same thing, right? Delta N plus NO. Excess electron concentration plus equilibrium electron concentration. We just got those values, you just remember. 10 to the 14th, okay? For holes, that's our doping concentration in the p-type semiconductor, right? It's kind of huge. This is like 10 to the 16th, right, for this problem. So basically, as you can see, this roughly gave us a value of 10 to the 16th per cubic centimeter, okay? So that's for the whole concentration, net whole concentration, okay? For electrons, the first term also gives us 10 to the 14th. The second term gives us actually 10 to the 4th, right? If you look into the last slide, and which is approximately 10 to the 14th per cubic centimeter, okay? So as you can see, for p-type semiconductor, my holes is like, this holes is like majority carriers. This really didn't get disturbed by those generation recombination, right? Just hold at the equilibrium value. But for minority carrier concentrations for electrons, as you can see, equilibrium value is 10 to the 4th, but right now I have 10 to the 14th, right? So basically, you see, it actually grow by orders. Right now, we want reevaluate the product of NP. So as we can see, it's 10 to the 16th times 10 to the 14th. So actually, it's up to 10 to the 30th. Comparing with the equilibrium state, which is actually 10 to the 20th, right, at room temperature. Actually, you can find that value is much larger, than the equilibrium values. Okay, so basically, this tells you about, basically under that case, the equilibrium state, that assumptions won't hold. Okay, so basically, the product of NP could be deviated from the Ni square very much. Okay, so basically, this is kind of simple. And for more general case, here I just list an expression here. For arbitrary injection levels, so we may not assume low-level injection. We can now no longer think the majority carriers, they won't get disturbed by the injection, by the generation recombination. But we just consider all the effects. So right now, eventually we get, there's a net rate of carriers recombination rate. So basically, still, basically the same definitions like del N over del T, also minus del P over del T. It turns out to be, right now I will have that. So basically, it looks more complicated. So if you look in the numerator, so basically, as you can see, this tells you about the difference between NP product as well with Ni square. So basically, you can once you can imagine, if the product of NP is larger than Ni square, so basically, the numerator become like positive, right? But the del P over del N, over del T, or like del N over del T. If this is positive, then this is negative. Okay? So what does that mean? Suggest like, okay. So probably I need to stop here. But that tells you del P is negative. So basically this net recombination is going to happen. Okay? So if the case is like product NP is smaller than Ni square, it tells you about del P over del T larger than 0. So basically, you would expect a net generation is going to happen to recover the system to its equilibrium state. Okay? I think that's pretty much of it. And I'm going to leave the summary part to Professor King next week. Okay?